Hello everybody and welcome back to the channel. It is like a good 10 degrees in Chicago today, so it's freezing outdoors. However, it's nice and toasty in my apartment because I've cranked up the heat. Or is it just you, perhaps? Oh god, I just cringed myself out so bad. Alright, no, let's do this video. Fuck this. Alrighty, so this is going to hopefully be a pretty fun video because I get to talk about one of my favorite technologies, Apache Flink. So this came out in 2011 originally, but I think this paper is probably from a few years later. For what it's worth, the paper that I'm reading as well is also not like a founding white paper. It's from some of the original contributors, but they're mostly just talking about a lot of the features of Flink when it's at a fairly stable point. So hopefully this covers the majority of the important stuff about Flink, but yeah, let's go ahead and do a deep dive otherwise. Worth noting that if you guys have noticed on this channel, I personally think Flink is the shit. So much so to the point that it's in my channel description, and when you look up my channel, people shit on me for it. Because apparently my absolute god tier systems design knowledge isn't enough to overcome hundreds and thousands of combined years of experience across engineers on the internet, which is a shame. But nonetheless, I do think Flink is a really cool technology. I think it has a lot of merits, and so we can go ahead and talk about them today. So, what is Flink? Well, actually kind of news to me because I always hear about it for stream processing. It is a batch processing system as well. You can run batch jobs with this thing in the same way that you would Spark, which is pretty darn good to know. And between those batch and stream processing jobs, they share common abstractions in the Flink programming model insofar as those jobs are modeled in a similar way. Even the batch jobs are modeled as stream jobs just with a finite stream because that's really what a batch job is. You have a stream and it's bounded in size. Number two is that Flink allows for stateful operators. So it took me a bit when I was first learning about this technology to really understand what that meant. What is a stateful consumer? What it really means is you're receiving incoming messages, and with each message, you're building up some amount of state. And that state needs to be persistent, right? So if your Flink consumer goes down, you need a way of making sure that that state doesn't just get thrown out and then you can never use it again. So imagine you were maintaining some sort of counter or some hash map or something like that. Basically, Flink is going to allow you to do this and do it in a fault-tolerant manner. So we have a bunch of operators in Flink. They get chained together themselves by intermediate streams. So not only are streams the input to Flink, but you also have many streams within a Flink job. They may not necessarily be on something like Kafka. They may be represented differently, but they're still there. And then also, most importantly, state is updated by every single input event exactly once. Note that I explicitly say state is updated, not the fact that each event is handled only once, but we'll talk about that in a bit. First question, why stream processing? We've mentioned this in a few of our papers before, and the really short answer is just it's faster, right? Like data tends to be produced in small bursts over time or in continuous events as opposed to like discrete batches. And so why wouldn't you try and get your insights kind of sooner? It's just the right thing to do. You're going to be able to get data faster to your data scientists or other people that care about it. There's this thing called the Lambda architecture that I've mentioned a few times on this channel, where the idea is, you can have streaming or stream processing for like approximate results, and then eventually, you'll go back and run some batch computation on an interval for exact results. Ideally, your stream processing can calculate the results themselves, but if for whatever reason there's just too much of a load here to do so, Flink is going to allow you to run both stream processing jobs as well as batch jobs, and so I guess you can do this with Flink just on one system without having to recreate the entire thing. Cool. Streams in Flink. So basically, a stream is just a grouping of records. It can be bounded, so like what you would have with a batch job, or it can be unbounded, right? And you never know when that stream is going to end. If I have a Kafka queue, for example, and I'm continuously publishing records to it, that's going to be unbounded. I never know when the end is. And so Flink jobs are basically just a DAG, a directed acyclic graph of a bunch of operators and streams that are connecting them. So streams can be internal to Flink as well, right? So for example, if we're doing some hash join between stream 1 and stream 2, we have this hash join operator, and then maybe the hash join results need to be filtered down. And so in order to pass those results from the hash join to the filter operator, you need a stream 3. And then finally, you may even have an output stream as well, a stream 4. Cool. So this is going to be a very packed slide, but it's not too complicated actually when we go through everything, so let's go ahead and do that. So number one is going to be that we've got a Flink client, so that's you writing your code, and then we've got a Flink job manager. The client's job is to take your code, convert it to a directed acyclic graph, as we saw on the last slide, send that to the job manager. The job manager then says, ooh, I see I have a bunch of operators here. Let me go ahead and take those and potentially partition them and put them on a bunch of different task managers. So it's going to schedule these operators. So now we've got all of our random nodes in our distributed cluster called task managers that are running Flink operators. And as these operators are actually running, maybe listening to some incoming data from a durable message broker, the job manager is consistently going to be sending heartbeats to and from each task manager to check if it's up or down. If it's down, we have to go ahead and do something in order to restore all the state that we may have lost. This is where something like checkpoint triggers comes in. The job manager on an interval is going to all of these task managers and basically asking them to checkpoint their state. The reason being that if one of the task managers was to go down, maybe all of a sudden we're going to reschedule that operator on a different task manager. We're going to reload the lost state from the last checkpoint, and we're going to replay the events since the checkpoint in that new task manager. Of course, the job manager itself, if it wants to be highly available and not a single point of failure, is also going to have to occasionally checkpoint its own state to something like Zookeeper so that it's persistent. And then, of course, if it's heartbeating to Zookeeper, Zookeeper can then detect whether it's up or down. And if it's down, all of a sudden something like a backup job manager can come up, it can read that last checkpointed state, and it can take over these Flink operations. Then finally, we've got something like durable storage, probably just going to be Amazon S3 or Hadoop, and that's where all of the checkpoints of the individual task managers themselves are going to be getting sent to. Great. Types of streams. So Flink, like I mentioned, has multiple different types of streams because, we have many operators that are chained together and we want certain properties of how they exchange data between one another. So the first type that is probably going to be the most common is going to be the idea of pipelined streams. So when we think about pipelining, the idea is, generally speaking, is when you're chaining two operations together, right? So maybe I'm mapping some sort of record to one property of that record. So maybe I'm doing a person to the person's name, and then maybe I'm doing a name to the number of characters in a name. And so the nice thing about pipelined operators is typically they can just run right on the same node. You don't have to do any data rebalancing or anything like that. But what that means is if you're running both of those operations completely sequentially, that these are blocking operators, right? So you get back pressure between consecutive operators because the first of those two operators is not going to handle another event until the second one has completed it, right? So I map the person to the name, I map the name to the number of characters in the name, and then now I pull another person in and run that again. So you get perfect back pressure there. That being said, Flink does have something called configurable buffer pools. So buffer pools are basically going to allow us to control how much back pressure these pipelined operators have on one another. So you can set two main fields for them. There's one that's called a size threshold. So basically, operator number one, the first operator in the chain, is going to produce a number of records up to a certain size. And when we reach that size, that's when we take that entire buffer of records, send it to the next operator. So the larger this gets, the more throughput we get, right? Because you get some sort of batching. It also means that, again, we get no back pressure here. So if the first operator happens to be really fast, it can basically just build out a bunch of results and then pass those all in batch to the second operator if the second operator is a little bit slower. We also have a second parameter called the time threshold. So the time threshold is basically saying, okay, maybe your size threshold is 100 kilobytes, but you're only at 20 kilobytes. But you set your time threshold to 30 seconds, and we've reached that time threshold. It's been 30 seconds. We haven't filled up this buffer. Let's go ahead and send it to our next operator anyway. So if you want to ensure the low latency of every single event record, the lower you set that time threshold, the lower your latency will be between one record when going from one operator to another. And then particularly for batch processing, there's also this concept of a blocking stream. And basically the idea here is it gets materialized possibly to disk or even like an external source of storage that's also going to be storing it on disk. But the whole point is, if we have a bounded stream, we first basically materialize the entire output of one operator and then only then send it to the next operator. So that there's no back pressure, but the point is you have to run that entire first operator. Okay, let's talk about Flink event ordering. So we've got all these streams in Flink, right? And originally, probably going to be the case that for every single input stream, like at the top level of the Flink DAG, every single record is coming in order for its actual timestamp, right? So that's going to be good. However, in Flink, we have a lot of things that are going to be pipeline breaking operators, right? Where you're actually sending data to multiple different places at once and receiving it from multiple different places at once. You can see that in my diagram below. Maybe we have a situation where this operator over here is sending events to both here and here, and same for this guy, also going to send events to here and here. When this happens, you can no longer make any guarantees about the ordering of events, simply because of the fact that these are going to be asynchronous communications. And when communication is asynchronous, or it's going over the network, you can't really make any guarantees about what event is going to get where first. You know that, if these two events were to, say, stay in the same stream over here, they would stay in order, right? Because we do have like FIFO processing within a partition. However, the second that we start getting to multiple partitions, things can get all mixed up. So it's important, generally speaking, that when you're writing Flink operators, you try not to rely on the order of the records coming in based on their timestamp, right? Like ideally, you want Flink operators that are deterministic, regardless of the order that events are coming in. Okay, now let's talk about what I would consider the really important part of Flink, which is going to be its checkpointing. So basically, like I mentioned, Flink has guarantees that for any record, it's only going to impact the state of every single operator that cares about it once. What that means is not that it's only going to get run once. That's kind of impossible, right? You would have to ensure that things never go down, they never fail. But in reality, what it means is we're going to use checkpoints. So if for whatever reason, we had some sort of operator or some sort of node in our Flink cluster of task managers that failed, we would basically revert every single operator back to its last checkpointed state that's fully checkpointed. The job manager is responsible for doing this. And then from there, we read every single input stream, from like the top level of Flink, from the associated offset of that checkpoint. So each checkpoint is itself associated with an offset of the input streams, or all of them, because there could be many input streams to a Flink job. And so you take a checkpoint corresponding to those offsets, and then you begin from those offsets again, and everything basically runs once. So we'll talk about how this is done so that it's actually correct. The idea is we want to take a consistent snapshot, right? It's very easy to take a snapshot. However, you want to be sure that all of the snapshots from the operators are at the same logical time, where logical time is basically representing one position of the input streams. So, it's important that basically all of the operators are perfectly synced up for their checkpoint. At the same time, it's really easy to take a screenshot, a checkpoint like this. However, you might incur a lot of costs due to coordination or contention or distributed locking, and we want to avoid that where possible. So how can we actually go ahead and do that? This is where Flink employs something known as snapshotting. So Flink is going to implement ABS, or asynchronous barrier snapshotting. So this is based off something called the Shandy-Lamport algorithm, although it's a little bit easier than that, and I frankly don't really feel like reading that full paper, at least right now. But the idea is this is going to generate consistent snapshots where we're seeing the operator state for every single operator at the same exact logical time from the input streams. So I'm going to try and explain this one as intuitively as possible because it's not simple, but I think I do really have hopefully a reasonable way of explaining it. So we're going to see. Basically, recall we have this job manager. The job manager on some interval is going to put something called barrier records into every single input queue of a Flink job. Right, so every single top level input stream. And then the idea is that this is going to produce checkpoints consistent across logical time. So what does a barrier actually represent? Let's imagine we had some incoming Kafka queue or something like that. Incoming queue. If we have a barrier right here, the operator is going to take a checkpoint to S3 when it sees the barrier. And so all of the state that it's going to have in its checkpoint is going to be the result of handling this message and this message, but not this message and this message. So if it were to go down and then it were to come back up again, basically we would only have to reread these two messages and just load the state from S3 corresponding to that barrier. So the question is now, basically because of the fact that we need to be able to replay these two events, it's important that all of our streams are durable in one manner or another. So what this means in practice is if we're materializing our streams to disk, they need to be on a replayable message broker like Kafka or Amazon Kinesis. Or if perhaps we're passing data from one operator to another, the producing operator has to have some sort of write-ahead log because maybe those records are just going over the network. Maybe we're not using Kafka as an intermediary. Cool. So one thing about this particular strategy of snapshotting that's not trivial at all is called alignment. So recall that for a Flink job, a lot of the time you're not just taking data from one incoming queue, but many incoming queues. We can do things like joins or merging or this or that require getting data from many different sources and potentially even different record types. So what does this look like as far as our barrier snapshotting goes? Well, I think it's actually not too bad. The idea basically is, let's imagine we've got Q1 over here, we've got Q2 over here, we've got an operator here that's merging these events together, maybe based on some common key that they have. We could be doing a hash join. Let's imagine we've now processed this one record over here on the top queue. And the next record that we process is the barrier in Q1. What we're now going to do as the operator is say, listen, I am not going to process this event until I see the barrier for all of my incoming queues. So we now have to process this guy, this guy, this guy, this guy, and this guy, and finally see the barrier. When we see all of our barriers, we then take our snapshot over here to S3. Note that it corresponds to both of these barriers, right? So the idea is this particular checkpoint is basically corresponding to if the barrier event was the last event that we ever processed and anything after them in any of the input queues was never processed. That way, we know that when we restart back up from this checkpoint, we can basically replay everything after the barrier events in every single queue. Now you might say, well, this is going to slow down computation, right, Jordan? Because now we can't process this guy until we're caught up on the other queue. Technically, that is true. However, it is not a complete and total pause, right? Because we are still processing these guys here. So we're still producing results, but it is true that we're not necessarily reading events from every single input queue at the time. Let's talk about iterative workflows quickly, because this is also an important part of stream processing, and it's going to continue to become more important as things like ML get bigger and bigger. So many types of jobs are going to require some sort of looping, right? It's the case for graph processing, maybe you're doing Pregel or some sort of like bulk synchronous processing algorithm, or machine learning for something like gradient descent. So maybe you're actually sending a bunch of events over some sort of stream, processing them, and then finally after you process that batch, you're doing some sort of iterative step and then processing them again. I guess the gist here is that, we said Flink models all of its tasks as a directed acyclic graph, and if we have a loop in a Flink workflow, that kind of implies that there's a cycle, right? So instead what Flink does is it does effectively, seemingly to me at least, make a cycle called a feedback stream, and so this is going to work nicely with checkpointing still because it's still abstracted with the stream, and also every single time that we have some sort of loop stream, the end of that loop, or basically, when we've completed an iteration of the loop, we inject something called a control event, which is going to act as a trigger to whatever the operator is that cares about this, that is going to trigger some sort of computation. So basically, imagine we've got some sort of like loop iteration here. So this would be called the tail edge of the loop. This guy over here is called the head edge. Now note that we've basically got incoming records from outside the loop, which is just going to be some alternative data source that are also coming into the tail through this edge right here. And then eventually, we have the loop records, which keep coming back and forth. And when we see record C, so our control event record in the tail, maybe we perform some sort of computation and persist some calculation elsewhere, either S3 or another output stream or something like that. So that's kind of at a high level how these iterative workloads are going to work. Okay, another really more important part of Flink in terms of its actual vanilla usage is going to be time. So there's three concepts of time of records in Flink. The idea is number one is event time, which is going to be the external published time of a record. Number two is going to be the ingestion time, which is basically when Flink first sees a record, so it can be any operator in Flink, not necessarily the one that's actively doing the time operation here. Number three is processing time, which is going to be that. So maybe we're computing some function that requires us to get the time of a record, we're going to use the current time in that operator. So obviously number three, though it is accurate for when we're doing processing, if you have many partitions of an operator that are distributed on many different task workers, then the timestamps that they produce may be inconsistent with one another because you can't trust distributed timestamps, generally speaking. So, all of these have pros and cons. Think about it for your own application, but yeah, generally just different types of timestamps. So one question that we often want to answer when we're running stream processing jobs is, what if we want to get a minimum bound on the times of events that we've processed, right? This is pretty trivial to do when you're only processing events in like one chain pipeline of queues the entire time. But maybe you have 2 incoming streams. How do we know for each operator what's the lowest event that it's processed, or like what is an event or a timestamp where we know there can be no incoming event with a lower timestamp than it. You know what? I'm just going to go to the next slide because it explains that concept a bit better. So if we have some operator and we have something called a low watermark for it. So if an operator says, hey, my current low watermark is time t, we know that we've processed all of the events in Flink that have possibly come through with a time less than t. Right? So it's a low watermark. It is a minimum bound of events that we could have processed. So the idea here to compute this at every single operator is to basically just inject a watermark event into each input stream and do so on an interval. So let's imagine these are input streams, Q1, Q2, and then we've got operator 1, operator 2, operator 3. So all of them have processed all events with timestamps lower than 5 at the moment. So let's go from here. So let's say our watermark entry with number 8 goes to operator 1. Okay, clearly operator 1, since it only has one input queue, has now processed all events with timestamps less than 8. So we can move our watermark to 8. That being said, when we pass the watermark of 8 over here to operator 3, we can't necessarily set the new watermark to 8 because it's possible we could have an event of 7 or 6 over here. That being said, when our watermark of 15 eventually gets to operator 2, we now say, okay, this guy's processed everything below 15, and then we pass 15 over here. We can now say, oh, you know what? I realize that we've processed everything up to 15, and we've also seen a watermark of 8. Let's go ahead and take the minimum of all of the watermarks that we've seen. So now our new low watermark is 8, right? Because we just did the minimum of 8 and 15. And now we can pass that 8 to any subsequent operators to say, okay, from this point on, we know we've processed all events with a timestamp less than 8. The final piece of this guy is going to be, or I guess the second to final piece of this guy is going to be stream windowing. So basically one really important thing that you can often do when using stream processing engines or stateful consumers is doing stream windowing, because we want to keep a bunch of buckets, assign records into each bucket, and then ultimately perform computations on them. Now at a high level, stream windows are pretty simple, right? It's just an interface that you have to define 3 functions. Number 1 is an assigner. You take every single record, you explain which bucket it goes into, probably based off the timestamp, but could be anything. Number 2 is some sort of trigger, where basically, maybe you have a bucket of 10 records, but the question is, when do you actually want to perform some computation on it? Maybe certain events are going to trigger that computation. Number 3 is going to be an evictor. Do events stay in the buckets forever, or do we get rid of them so we don't, have memory leaks and casually just blow up our memory usage? So Flink is going to have many pre-built windowing implementations, like sliding windows and hopping windows and all that fun stuff, and it makes it really easy for you to use. But if you do want to build some sort of more complicated window, you can do so. They also have global windows, which I guess rather than just being on one isolated partition, can span many of them. The problem with that is that now, of course, you need to do coordination when making these calculations. Like if you want to create a sum of all events in your window, and that window is distributed across multiple different nodes, now all of a sudden you need to do some kind of MapReduce-like operation. Okay, the final piece of this video is going to quickly touch upon batch processing in Flink. The main idea here is that even though all of these tasks are still converted to a DAG and represented as a DAG, because they're treated as bounded streams, right? They're just not infinite streams. Under the hood, we can do different stuff to optimize these a little bit more, and if you watch my Spark video, I think that's kind of a better one to watch here. The idea is, rather than just occasionally checkpointing your job, you can actually kind of take note of what operations you're performing, whether they are pipelined operators or pipeline breaking operators, and as a result either checkpoint those or just replay certain computations. So generally speaking, if you have something like a narrow dependency or a pipelined operator, you just want to replay computation. If you have a pipeline breaker or a wide dependency, that's when you want to do checkpoints right after you finish that computation. You can do query optimization as well in Flink, or I shouldn't say you can do it, but Flink will do it for you, based on things like partitioning and sorting information. Flink is going to allow you to write UDFs, or arbitrary functions, and as a result of doing that, it becomes hard for it to do optimization, because like in a SQL query optimizer, it's a pretty limited set of functionalities, so you can optimize stuff. For Flink, you're writing your own code, and there are wrappers around it, but you're writing your own functions, and so it's hard to optimize those perfectly. Okay, let's conclude. Why does Jordan like Flink so much? Well, hopefully I got my point across here. Flink is going to allow us to do asynchronous computation. It's still going to allow us to get faster insights than batch processing. It is still going to ensure fault tolerance for all of our messages and ensure that they are processed exactly once. That's the big thing for me, which is why I like him so much in these systems design interviews, is because you can go down a rabbit hole all day of being like, oh, I have this consumer for Kafka, but I now need to make sure that it doesn't go down, or I need to make sure that my state that I'm building up gets persisted. No, you don't. You can use Flink. And I don't really feel like spending 20 minutes during the course of an interview explaining how to checkpoint my state and, get it right and don't have any race conditions. I would rather just use an existing technology. This is why I talk about it all the time. This is why people hate on me. Such is life. And, I'm just going to go cry about it. Point is, that checkpointing is using asynchronous barrier snapshotting. And whenever things do go down, you basically restore the state from the last checkpoint, replay all events since the last checkpoint, and you're good to go. I hope you guys enjoyed this video. People have been asking me to do this deep dive for a while, I think, just because I talk about this technology so much, and it's been a pleasure to get to cover it a little bit more. Anyways, guys, I hope that you all have a great week, and I will see you in the next one.